As for this, I think the third installment of the videos for chapter 5, where we are exploring stereochemistry, so we can understand the 3D nature of these molecules. Now, the earlier, right, in the semester, we talked about cis and trans stereochemistry, where I hope it makes sense to you. Like, for instance, these two methyl groups are cis to each other, right? These are cis relationships because they're on the same side of the cyclohexane. They're on the bottom side or the beta side of the cyclohexane. This would be this. If this methyl group was actually pointing this way, equatorial, and then these two methyl groups would be trans because the two methyl groups would be on the opposite sides of the cyclohexane. But those terms, cis and trans, it's just referring to relative stereochemistry. They're either on the same side or the opposite, right? But when it comes to chiral molecules, which actually this is a chiral molecule, that's not enough to completely describe what this molecule should look like, because especially if we are comparing this trans versus that was bad, that trans dimethyl cyclohexane, right, like these two actually are mirror images of each other. These are enantiomers of each other, and so therefore for me to say that this is trans is not enough to describe which of these enantiomers we're talking about. So we need to have a way of describing absolute stereochemistry. That's what we mean by relative stereochemistry. It's not enough for chiral molecules. So we use the Cahn-Ingold-Prelog convention, which is the IUPAC convention, or International Union of Pure and Applied Chemistry Society, to assign either R or S configuration to the each chiral center. So that's what we do. Okay, and so here's the Cahn-Ingold-Prelog convention, the two steps, okay, that we're gonna go through. So first step, assign a priority to each group that's on the carbon, as in this, we mean that this is the chiral center. And for this, the higher the atomic number, the higher the priority. That's the priority that we're gonna assign to the to each of these groups. Okay, so for instance, here at this chiral center, we're comparing hydrogen, fluorine, chlorine, and a methyl group. So of those, the highest atomic number, of course, is going to be chlorine. Okay, if you go look up the those elements in the periodic table, and then fluorine, and then carbon, and then hydrogen. So it's in that order. At this point, if there's a tie, then you examine the next atom in the chain. Like if there was another carbon here and a carbon here, you go to the next atom in the chain, which on the methyl group will be hydrogen. And if there's a double or triple bond from these atoms, then you count those double bonded atom twice for that high priority purpose. And then we'll talk more about this later. Now, the second step is place the lowest priority group or atom away from you. In this specific case, we already have the lowest priority group away from us, pointed away from us, so that's going to work out just fine. But what we mean by, like, we need to put the lowest group away from us. Let me switch to the camera view. Oops. Hi there. So if this is the chiral center we're looking at, right, then you need to, this is a hydrogen. if you're looking at the molecule like this, you want to rotate it so that you're looking at it like this, where the hydrogen is pointing away from you. Well, it's pointing at me, but I'm assuming it's pointing away from you, right? That's the orientation you need to have it. And then you, let's say the priority groups go 1, 2, 3. Then this is rotating in the 1, 2, 3. 1, 2, 3. So it's in the 1, 2, 3. In the same direction as when, if this was like a steering wheel, it's when you turn right. So if it's going clockwise or turning to the right, the assignment is R. And if you are, if it's the other way around, you might think it should be L for left, but it's actually S for the Latin word sinister, which means left in Latin, because in the old days, some people had superstition that it's kind of a sin to be left-handed. Okay, and that's just a Latin thing, but so that's how you assign it. So the second step, you gotta put the fourth group away from you. Now, the most foolproof way to do this is to build a molecular model and then rotate it around so that the lowest group is pointing away from you. And then what you do is, if the assignment would be R, which is actually for the word rectus in Latin, which means right. If you follow the priority 1, 2, 3, oops, and that is pointing clockwise, or like as if you're turning right, right? So think about the steering wheel of driving, right? And then if it's the other way around, that's left or sinister in Latin, which so if this is counterclockwise. All right, so going back to our example, I hope it makes sense that it goes 1, 2, 3. So that's the, in this direction, which is opposite of clockwise. It's counterclockwise. It's that you turn your steering wheel that way when you turn left. So this is an S assignment. Okay, hope that makes sense. Here's a couple more examples. Let's say we have this molecule, okay. Now, this would be a little bit more interesting case, perhaps, because when hopefully you can identify that this is a chiral center. So we will go to put priority list. Now, bromine is obviously number 1, hydrogen is obviously number 4, but you notice that these two are both carbon atoms, so it's a tie here, right? So then when you need to look at the atoms that are attached to this carbon. So here's carbon attached to that, as well as 2 hydrogens. If you look at this carbon, there's a carbon attached to that, as well as 2 hydrogens. So even if you go out one more atom, they're still tied between left and right. Now, when you compare these 2 atoms, these 2 carbons, this carbon only has 3 hydrogens attached to it, whereas this carbon has a bromine attached to it, which of course has a higher atomic number and a priority. And so for that reason, this carbon gets a higher priority than this other carbon. Hope that makes sense. And so this now is also S. Now, I hope this makes sense to you, but if you draw the mirror image of this, the assignment for the enantiomer should be the other way around, and this should be R. Oops. Okay, and indeed, you should be able to verify that with the priority list. Now, here's a little more trickier situation, perhaps. Like if you had this molecule, can we assign R and S? Well, let's think about this situation. So obviously this is your chiral center, and priorities are going to be a little tricky because all three atoms attached to that are carbons. Well, there's a hydrogen as well, but so what you need to do is you need to sort of take inventory of what each atom is attached to. So this carbon is attached to a carbon, but we count that twice because of the double bond. So this is attached to 2 carbons and a hydrogen. And this carbon, on the other hand, is attached to a carbon and 2 hydrogens here. Hope that makes sense. So CHH. Now this carbon is attached to just 3 hydrogens. Right. So for that reason, we could say that the priority is going to be 1, 2, and 3. So that's great. But fourth priority group, the hydrogen is unfortunately pointing at us. So what do we do? Again, the most foolproof way to solve this would be to make a model of this so you can flip the molecule around so that the hydrogen is pointing away from you, and then you do your 1, 2, 3. However, if that's not feasible, like it's an ACS exam for which you're not allowed to use the model kit and stuff like that, or you're on a deserted island and you're trying to assign R and S configuration, because of course you would do that on a deserted island, then here's another method. Okay, so the priorities go 1, 2, 3, so it looks like this is R, right? But knowing that the lowest priority group is pointing in the wrong direction, pointing at us, it's not in the back, so you have to take the opposite. So maybe I'll write that out. This appears to be but the lowest priority group which is hydrogen in this case, it's not in the back. So you take the opposite, so this is actually S configuration. Hope that makes sense. And in class we'll practice with these 2 more examples, okay, by naming these guys. So I'll see you guys in the next video.